Hello everyone, in this video we'll be solving problem 530, minimum absolute difference in a binary search tree. The problem statement is, given the root of a binary search tree, return the minimum absolute difference between the values of any two different nodes in the tree. In example number 1, if you look at the values of each node, the minimum difference is 1, which is between node 1 and 2 or node 2 and 3. Hence the output is 1. Similarly, in example number 2, the minimum diff is also 1, which is between node 0 and node 1. I hope you were able to understand the problem statement. Let's switch to whiteboard and discuss how we can solve it. The simplest way to solve this problem is using the naive approach, where we'll iterate through all of the nodes in the given binary search tree, save it to a collection first, and then we'll sort it in an ascending order and compare the difference between the adjacent nodes. The idea is that if the array is sorted, the minimum difference can be found by comparing the values of the adjacent numbers. There's no point in comparing the first entry with the last one, as the difference will not be minimal. This approach will help save some of our compute time. If we were to apply this logic to the given input, the sorted array will have 1, 2, 3, 4 and 6. Starting with I is equal to 1, its corresponding value is 1. We'll compare it with the next value, which is 2. The difference is 1, and we'll save it in the variable. Then we'll increment our I pointer. So now we are looking at 2, comparing it with 3. As the difference is not smaller than the current minimum, we won't save it and continue the iteration further until the end. With this solution, our time complexity is O of n plus O of n log n plus O of n, where the first O of n is iterating through all of the nodes in the given binary search tree. The n log n is actually for sorting, and the last one is to iterate through the sorted array to identify the difference. Let's simplify it to O of n. While the space complexity is O of n, as we are maintaining this sorted array to calculate the difference. As we have this additional overhead of maintaining this sorted array, which is causing an impact to our space complexity, let's think about how we can improve the solution. Another way to solve this problem is by using in-order traversal, in which we first process the left node, then the root node, followed by the right node. One important concept about binary search trees are, if you look at the values of the root node and compare it against its left and the right tree, the value of the root node will always be greater than its left node, while less than the value of its right node. So if we use the in-order traversal to iterate through all of the nodes in a given binary tree, the sequence will be sorted by default. So we can save some additional operations of sorting the output. All we need to do is go to the very left node of the tree, compare its value against the root node, calculate the difference, and see if it is the minimal difference that we have calculated in the past iterations. If it is, then save it. Similarly, we'll then move to the root node and compare its value against the right node. Let's simulate this by running a couple of iterations on this given input. Starting with the root node 25, we'll iterate to the leftmost node of it, which is node 7. As node 7 does not have a left leg, there is nothing to process. So we'll process the root node, which is node 7, and then go to the right node. As we need the node to compare its value with the next node, we'll create a new variable, call it previous, and save node 7 in it. As node 7 is processed, we'll go to its parent, which is node 15. We'll save it to the current variable. Now we'll compare its value against the previous node that we have saved, see the difference, and if it is smaller, we'll save it in a new variable minimum. As minimum doesn't have a value, we'll save 15 minus 7, that is 8 in this variable. As this iteration is done, now we'll replace the previous value to 15, and the current will be the right node of node 15, which is 18. The current difference is 3, which is smaller than the last value that we have saved. So we'll replace it and continue forward. For the next run, previous will become 18. Now we are moving up the ladder to node 20. The 20 becomes the current node. The difference between current and previous node is 2, which is smaller than the previous minimum value. So we'll replace it and continue forward. Now we are looking at the right node of node 20. So we'll replace the previous to 20, and the current will be 23. Similarly, after processing node 23, we'll then process node 25 and all of the node on its right hand side. If you look at the sequence in which we processed the nodes, we started with 7, followed by 15, then 18, followed by 20, 23, 25, 32, and 40. You can see that all of these numbers are in ascending order. So we were processing the nodes in ascending order without having to run the sort operation. With this solution, our time complexity is O of n, where n is the number of nodes in the given binary tree, and the space complexity is O of 1, as we are only creating these two variables to maintain the current and the previous node while returning the minimum as the output. I hope you were able to understand this explanation. Let me show you how we can implement this using C#. Here is the C# solution. I've created this private method in order traversal which accepts the root, the minimum diff, and the previous node that we have iterated as an input. The first check I do is to compare if the root node is null. If it is, then I'm returning the minimum diff and previous node as is without processing anything. I'm then recursively calling the in-order traversal method again, passing the left node of the root node with the minimum diff and previous that we get as an input. The output of this is going to be minimum diff and prev. If the previous is not null, then I'm taking the absolute difference between the root node and the previous value and comparing it against the minimum diff. Whichever is smaller is being saved back into the minimum diff variable. After processing the root node, then I'm saving the root node into this previous node value and calling the in-order traversal method again, passing the right node of the root. After the iteration is done, we'll have the minimum diff in this variable which is returned on the main method. This method, when submitted on LeetCode, beats 100% of the submissions in terms of runtime and 52% in terms of memory. Thank you for watching this video. I hope you were able to understand this explanation and the code. The link to the code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.